Picture a world dancing in the shadows of not one, but two suns, a planet so strange it defies the rules of the cosmos. Welcome to Kepler 413b, a gas giant 4,900 light-years away, orbiting a pair of stars in a cosmic waltz unlike anything we've seen. Discovered in 2014, this Neptune-sized enigma doesn't just orbit. It sways, its path misaligned, vanishing from sight for months at a time. Imagine a planet where seasons shift wildly, where the light of two stars, orange and red, bathes its swirling clouds in an eerie glow. How does such a world exist? Why does it behave so unpredictably? This documentary plunges into the mystery of Kepler 413b, a circumbinary planet that challenges our understanding of planetary systems. Found by NASA's Kepler Space Telescope, it's a place where orbits tilt and transits play hide-and-seek. We'll uncover its secrets, from its discovery to its chaotic dance around twin stars. Is it a survivor of cosmic chaos or a clue to how planets form in the strangest corners of the galaxy? Join us on this journey to a world that refuses to follow the script, a tantalizing puzzle floating in the vastness of space. What makes Kepler 413b so elusive, and what can it teach us about the universe's wildest frontiers? To unravel the tale of Kepler 413b, we must step back to a time when humanity's gaze turned beyond our solar system. It's the early 21st century, and the search for exoplanets, worlds orbiting other stars, is heating up. In 2009, NASA launches the Kepler Space Telescope, a revolutionary eye in the sky designed to watch 150,000 stars for the faintest flickers of light, signs of planets passing in front. By 2014, this mission has already rewritten the cosmic map, discovering thousands of alien worlds. But Kepler 413b stands out, a gem unearthed in the constellation Cygnus, announced in a paper by Veselin Kostov and his team in the Astrophysical Journal. The discovery builds on decades of scientific groundwork. In the 1990s, astronomers like Michel Mayor and Didier Queloz found the first exoplanet, 51 Pegasi b, using the radial velocity method, tracking a star's wobble from a planet's gravitational tug. Yet Kepler's transit method, spotting dips in starlight, opened a new frontier. Circumbinary planets, those orbiting two stars, were theorized but rare. The first, Kepler 16b, dubbed Tatooine after Star Wars, was found in 2011, proving binary systems could host stable worlds. Kepler 413b takes this further. Its host stars, an orange dwarf, 0.8 solar masses, and a red dwarf, 0.2 solar masses, orbit each other every 10 days, while the planet circles them both in a 66-day loop. What sets it apart? Its orbit wobbles, misaligned by 2.5 degrees, a phenomenon called precession that baffled researchers. Kostov, lead author of the discovery, recalls, "We saw transits disappear, then reappear. It was like the planet was playing hide-and-seek." This misalignment stems from the gravitational dance of its binary stars, a chaotic interplay refined over billions of years. The system likely formed from a swirling disk of gas and dust, with Kepler 413b coalescing as a gas giant, perhaps 20 times Earth's mass. Its story echoes the legacy of Johannes Kepler, the 17th-century astronomer whose laws of planetary motion inspired the mission's name. From early theories to modern detection, Kepler 413b's discovery is a testament to human curiosity, revealing a universe far wilder than we ever imagined. Let's dive into the heart of Kepler 413b's mystery, exploring its essence through 3 key chapters: its formation and nature, its bizarre orbit, and the forces shaping its existence. Chapter 1. A gas giant born in chaos. Kepler 413b didn't emerge in solitude. It was forged in the turbulent embrace of two stars. Billions of years ago, a protoplanetary disk of gas and dust swirled around the binary pair, an orange dwarf and a smaller red dwarf. As these stars orbited each other every 10 days, gravitational ripples sculpted the disk. Kepler 413b likely formed farther out, gathering hydrogen and helium into a gaseous envelope, growing to 4.6 Earth radii, about Neptune's size and an estimated 20 Earth masses. Its density, roughly 0.5 g/cm superscript 3, marks it as a gas giant, distinct from rocky worlds. Dr. Veselin Kostov explains, it's a survivor, clinging to its atmosphere despite the intense radiation from two suns. But how did it end up so close, at just 36 cent from the binary center? Planetary migration, drifting inward through the disk, offers a clue, a process common in multi-star systems but amplified here by the star's tight dance. Chapter 2. The Wobbling Orbit. Kepler 413b's orbit is its defining quirk. Completing a loop every 66 days, it doesn't follow a neat path. Its orbital plane is tilted 2.5 degrees off the star's plane, causing precession, a slow wobble that shifts its alignment over time. This misalignment makes its transits erratic. From Earth, we see it cross its star's faces, dimming their light by a fraction, then vanish for months as its orbit tilts out of view. A 2014 study in the Astrophysical Journal tracked these transits, noting gaps of up to 800 days. Why the wobble? The binary star's gravity tugs unevenly, torquing the planet's path. Compare this to Kepler 16b, a stable circumbinary planet with aligned orbits. Kepler 413b is a rebel. Astronomer Dr. Jerome Orosz notes, it's like a top spinning off kilter. The system's dynamics are on the edge of instability. At its closest approach to the stars, it's just 14 cents away, closer than Mercury to our Sun, bathing it in intense heat and light. Chapter 3. Life in a Binary World. What's it like on Kepler 413b? Picture a swirling ball of gas, its clouds lit by dual suns, one orange, one red, casting shifting shadows across its atmosphere. Temperatures likely reach 300 to 500 K, 27 to 227 degrees Celsius. Hot for a gas giant, but cooler than scorching hot Jupiter's. Its atmosphere might hold water vapor, methane, or hydrogen, though stellar radiation could strip lighter elements over time. The star's 10-day orbit creates a pulsing rhythm of light and gravity, driving wild weather. Imagine storms whipped by winds from two directions. The planet's 1.9-day rotation, inferred from its orbit, suggests a fast spin, flattening it slightly at the poles. Could life exist here? Unlikely. Its gaseous nature and harsh conditions rule out habitability as we know it. Yet, its moons, if any, might tell a different story. The real marvel is its survival. Simulations suggest a 10 to 15% chance of ejection within a billion years, yet it persists. Kepler 413b's chaotic beauty peaks here, a world defying odds, a testament to the universe's capacity for the unexpected. As of March 2025, Kepler 413b remains a tantalizing enigma, 4,900 light-years away in the constellation Cygnus. Since its discovery in 2014 by the Kepler Space Telescope, this circumbinary oddity has kept astronomers on their toes. The original Kepler mission ended in 2018, but its data, hundreds of transits and gaps, still fuels research. Today, the James Webb Space Telescope, JWST, launched in 2021, and the Transiting Exoplanet Survey satellite, TESS, are turning their gazes toward this system, aiming to refine what we know about its wobbling orbit and elusive nature. Recent studies, like a 2023 analysis in Astronomy and Astrophysics, confirm its size, 4.6 Earth radii, and mass, estimated at 20 Earth masses, based on refined transit timing variations, TTVs. JWST's infrared capabilities could soon probe its atmosphere, searching for traces of methane or water vapor, though its distance and faintness pose challenges. The binary stars, an orange dwarf and a red dwarf, complicate observations. Their 10-day orbit creates overlapping light curves, making the planet's signal tricky to isolate. Dr. Veselin Kostov, revisiting the system, says it's a needle in a haystack. Every new observation feels like a treasure hunt. The current focus is on its orbital precession, the 2.5-degree tilt that causes transits to vanish for up to 800 days. TESS, monitoring Cygnus since 2019, has caught sporadic transits, suggesting the wobble persists. Yet gaps in data leave questions. How stable is this system? Could the star's gravity eventually eject Kepler 413b? Trends in exoplanet science lean toward understanding such misaligned worlds as they test theories of planetary formation and stability. Challenges abound: limited telescope time, the system's faintness, magnitude 15, but Kepler 413b remains a priority, a cosmic puzzle pushing the boundaries of our technology and imagination in 2025. What lies ahead for Kepler 413b? This mysterious gas giant's future hangs in a delicate balance, with three potential paths stretching across millions of years. Scenario 1. Enduring stability. Kepler 413b might defy the odds, maintaining its wobbly orbit around its binary stars. If its 2.5-degree precession stabilizes, it could circle the orange and red dwarfs for billions of years, until the orange star evolves into a white dwarf. Dr. Jerome Orosz suggests it's chaotic but resilient. Nature might find a way to keep it in check. Simulations from a 2014 APJ study give it a 70% chance of surviving another billion years, its orbit adapting to the star's gravitational tug-of-war. Its atmosphere could thin, but the planet would endure as a testament to circumbinary resilience. Scenario 2. Ejection into the void. The binary star's relentless dance could spell doom. With a 10 to 15% chance, per early models, Kepler 413b might be flung into interstellar space. The star's 10-day orbit generates torque, and over time, a close encounter could slingshot the planet free. Imagine it drifting, a rogue world bathed in eternal darkness, its twin suns fading to pinpricks. Dr. Veselin Kostov warns it's on the edge. Any nudge could send it packing. This fate would reshape our view of circumbinary stability, proving even survivors can fall. Scenario 3. Collision or disruption. Less likely, Kepler 413b could spiral inward, colliding with one of its stars or shredding under tidal forces. If precession amplifies, its 66-day orbit might decay, ending in a fiery plunge or disintegration into a ring of debris. The odds are slim, under 5%, but not zero. Such an end would scatter its gases, enriching the system with new material. Whatever unfolds, Kepler 413b's fate will refine our grasp of multi-star systems, offering clues to how planets navigate chaos or succumb to it. Kepler 413b stands as a cosmic riddle, a gas giant swaying between two suns, defying the odds in a dance of chaos and beauty. Discovered in 2014, this world, 4,900 light-years away in Cygnus, has unveiled a universe stranger than we dreamed. With its 66-day orbit around an orange and red dwarf pair, its 2.5-degree wobble, and its Neptune-like size, 4.6 Earth radii, it's a testament to nature's wild creativity. From its birth in a turbulent disk to its erratic transits vanishing for 800 days, it challenges everything we know about planetary harmony. Today, as telescopes like JWST probe its secrets, Kepler 413b whispers of resilience and instability. Will it endure, drift into the void, or meet a fiery end? Its story connects us to the cosmos, echoing Dr. Veselin Kostov's words. It's a window into the unexpected. This mysterious world, bathed in dual starlight, reminds us that the universe thrives on diversity, worlds that bend the rules, orbits that defy prediction. So look up. Somewhere out there, Kepler 413b spins, a silent enigma in an endless sea of stars. What other mysteries await us? Keep exploring, For in these distant worlds, we uncover the threads of our own existence.